Alright, let's take a look at conservative forces and potential energy and the different types, and then let's go right into the conservation energy. So let's finish the toolbox for this chapter, and really these last two sections are going to make everything easier for us. But we got to start by knowing and defining a conservative force, and I'm really going to be reading this right out of the book almost. They say it pretty elegantly. If the work of a force is independent of the path and depends only on the initial and final positions, then it's conservative. So independent of path and that's the work of a force we're talking about. Remember, force is F dotted into dr are the works, right? The work from 1 to 2. Well, if we only are dependent on the position of it, then we don't have to, then we can call it conservative and use conservation energy. We can still use the conservation energy methods with non-conservative forces, and I'm going to show you how. But for now, let's just take a look at some conservative forces. And some examples of these would be like the weight of a particle. We talked about how it doesn't matter if you take a particle through space, the x and only the direction you're taking it and that lines up with the gravitational force. So if this delta y here, if we have mg pointed down and we got some delta y that it traveled from 1 to 2, all that matters is that delta y, and we showed that earlier. And I'm going to show you another way how to prove that too, with what's called the del function. Del operator, sorry. Another example would be a spring force, or the work done by a spring force. We're going to see that it doesn't matter if we just look at where it is before and where it is after. We can just look at how much the spring is stretched at each position, and it doesn't matter about the force that the spring puts out at all. It's a fantastic thing, and you'll see the energy is always positive in that case too. What else? We cannot say friction, so friction is not conservative. And really the common sense thing to this is that it turns into heat, so we lose it, right? But also the work done by frictional force does depend on the path. The longer the path, the greater the work. So the fact that we have mu k times the normal force and some delta x on the path, the longer this is, I can't spell, the longer that is, the more work we're going to be doing. It's not conservative. And we are literally turning it into, we are dissipating body, we're dissipating heat from the body, and that is the work. Okay, let's talk about energy. We haven't really quite defined it yet. We've seen we can have a couple types. We've really just worked with kinetic energy so far, and then looked at other things as work. Well, we definitely have kinetic as 1/2 mv squared. We'll see there's a rotational term also. If something has mass, and that mass is spread out over maybe like a cylinder, then we also have to consider the moment of inertia and its rotational energy, but not yet. So energy definition is the capacity to do work. And some real basic example again right here is looking at the weight of a particle. If you lift something up into space, it can turn that into kinetic energy. That's a chain. Remember, work is defined also as the change in kinetic energy, which really just means a change in speed. So if I have some gravitational potential energy, such as you might recognize mg delta y or something, and I will define that in just a second too. That can turn into some 1/2 mv squared by falling back through space. So work is equal to the change in kinetic energy, and literally that energy is the capacity to do work. In this case, it just turned into another type of energy. But what about a spring? It really just turns into another type of energy too, but a spring also, literally, you push on it and it stores energy kind of like a battery, and now has the capacity to do work. And if you pull on the spring and stretch it, the same exact thing. It's got energy bound up in it, and you can turn it into something else. It can do work or turn into another type of energy. So the most common two would be the gravitational potential, like we've seen. Gravitational potential energy. And we are going to call that V sub G. So now, remember, I've been showing you T1 plus V1, but we haven't really seen the V1 in the book yet. Plus is equal to T2 plus V2. I was just showing you where we were headed to kind of clarify what we were working for. Well, here it goes. Here's one form of potential energy. The book is going to call it Wy, or the weight times how high up from some datum it is. I'm going to call it mgh or mg delta y usually. So now comes the point where we now have to measure a reference point for everything. And I typically pick the ground, but you don't have to. I try to keep negative signs out. If a mass is now located some delta y above the ground, that now has the potential mass times the acceleration due to gravity times that distance delta y. Alright, same thing as the work it can do if it fell. It's exactly equal to the work it could do. Let's see what else we got. Let's look at elastic spring energy a little bit more. We saw that springs can do work, but really, in my opinion, if we can work with them using conservative forces and conservation of energy, it's a lot easier. And we have seen a negative sign before, but really, if we use conservation of energy, the spring forces, or the spring energy, is always positive. You just got to put it on the right side of our equation. Our T1 plus V1 is equal to T2 plus V2. How far is the spring stretched in its initial state? And how far is it stretched in its final state? And I'm going to go over all that when I introduce chapters 14.6, right after this. But let's take a look. If we had this is maybe a wall that the spring is fixed to. Let's say this is its equilibrium position, and let's start with the equilibrium. If a spring is at its equilibrium position, there's no force, so it has no potential to do work. The elastic potential is 0. Now, if I were to elongate that spring from its unstretched position, we would get a potential equal to, positive, don't have to worry about the minus sign, 1/2 ks squared, where this is s. And if we compress that spring, and this becomes, maybe if this is s 1, let's call this S2, then our potential is still a positive 1/2 K S2 squared. We just got to look at the before and after. Where is it in space? Put that on the left hand side. What are the coordinates and what kind of energies it have after? Put that on the right hand side. It goes over then what's called a potential function. And all that's really doing is combining the gravitational potential and the elastic potential, so that when we write T1 plus V1 is equal to T2 plus V2, we now need to make sure we include both of those. So I typically write out all the terms, even if I don't need them, just to make sure I don't miss something. This is our T1. Our potential now could have some mg, maybe Y1, plus some elastic potential, x1 squared. Or it really doesn't have to be the x direction, it's just some amount of stretch, so let's call it s. And that could equal some final 1/2 mv squared, plus some new coordinate in space in the y direction, giving us a different potential, plus maybe a different spring stretch. Alright, this is the conservation of mechanical energy. That is T1 plus V1 is equal to T2 plus V2. These are the same. I'll typically take the time to write it out. If I don't need this thing, and it comes back down to the surface of Earth, so I don't need potential energy, and maybe the spring isn't stretched initially, so I can just cross those out. It really simplifies things. Mass often cancels out. This is really my preferred method to try to attempt to solve a problem, and that's how I'm going to try to handle it. So that gets us into 14.6, the conservation of energy. Alright. What does this mean? Well, we just look at a before situation, and what's its velocity before, what's the mass's y coordinate, and what is the stretch in the spring. And then we see an after condition, and we may have some of these initial conditions on both sides of the equation, who knows. And we might want to find the velocity, but we will know its y coordinate and the spring stretch in the final state. Now we can add in non-conservative forces also. If we do T1 plus B1 plus the summation of the work done from 1 to 2 for non-conservative, and that's going to be equal to T2 plus V2. And this is what I'm talking about. We just got to put this in as plus or minus work. And does it add energy? That's plus. Does it speed up the system? Does it raise it? Is a force doing some pushing on it, making it speed up or something? That's adding it. And if it's taking away energy, that's going to be a minus sign. So this is my preferred way to solve any of these conservation of energy problems. And of course we can extend this to a system of particles. Alright, I think my video time is about to run out.